Electrostatics, electrostatic materials. In this lecture, we will briefly talk about classes of electromagnetic materials, but not being a material class, I don't want to spend too much time there. Instead, I want to move on to the boundary conditions, and this is where we have an interface between two different materials, and if we know the field on one side of that interface, we'd like to derive a set of equations where we can figure out the field on the other side. And so we'll look at dielectric interface, conductor dielectric, and we'll also discuss something called refraction because the fields appear to bend at that interface. And then we'll work an example that'll hopefully illustrate all of this. General classes of electromagnetic materials. For this class, we're just going to talk about three different classes of materials because this affects how we'll solve equations. The first type are insulators, and we define insulators where the conductivity is very, very small, much less than 1. So inside of an isolator, it's all bound charges, no free charges to conduct a current. So insulators oppose current. Most dielectrics that we work with are insulating, so plastics, paper, wood, ceramics, almost all of these are insulating materials. On the other end of the spectrum are conductors. Most metals are conductors, and this is defined where the conductivity is a very, very large number. There's lots of free charges, electrons that have broken away from their atoms and can conduct a current. So these easily conduct electricity. So things like copper and silver and gold, all these metals have very high conductivity. Then there are materials in between the two that we call semiconductors. Some of these are switchable, like silicon. We make computer chips and transistors, and we can switch and tune so we can make the conductivity high or low. And so it's not really fair to call these insulating or conducting when they can do a little bit of both. So these are the broad categories. In this class, we don't really talk about the semiconductors. We just approximate something either as a perfect insulator or a perfect conductor. On to the boundary conditions, and here we're talking about a dielectric-dielectric interface, so no conductivity here. First, I'd like to answer the question of why we even need boundary conditions. Well, most often when we solve a problem, we're solving differential equations. We seem to prefer these over integral equations, and these differential equations involve derivatives. Well, if we have the interface between two different materials, that is a discontinuity, and derivatives explode at discontinuities. So in fact, we can't solve a derivative across an interface. So what do we have to do? We separate our problems into homogeneous segments. We solve our differential equations in those homogeneous segments, so that way the derivatives don't explode. And then when we're done that, we assemble our answers, we stitch them together by matching the boundary conditions. And usually this means that the function values on either side of an interface are equal. And that way the overall function is continuous all the way through the device. Interestingly, integral equations don't require boundary conditions unless they contain some derivatives. But if it's a pure integral equation, no boundary conditions. So if we want to derive expressions for the boundary conditions, it makes sense then that we would derive them from the integral equations, because clearly whatever's going on, that information must be contained in the integral equations if they don't need boundary conditions. So that's where we'll start. So we have the line integral E dot dl. We're going to use this to derive the boundary conditions for the tangential components of the fields. And then we have integrating the flux. We will use this to calculate our boundary conditions for the normal components of the electric fields. So here's our setup. We have the interface between two different materials. I could have drawn this as a flat interface. I drew it as a curve because I want to convey this really applies. When we're talking about boundary conditions, normally we're talking about an infinitely small point along that interface. So on the first side, on the top side, we'll say this has a permittivity epsilon 1, and then the second medium will have a permittivity epsilon 2. Now, let's say we know the electric field on one side of the interface. We know E1. We'd like a set of rules to be able to calculate immediately E2. Those are our boundary conditions. It's going to be useful to express our vectors in terms of tangential and normal components. Make no mistake, if we pick a side of the interface, the only vector that's really there is this E1. But we can think of that as the sum of a tangential component, which is parallel to the interface, and a normal component, which is perpendicular to the interface. And we could do the same thing on both sides. So we'll have a tangential and normal component on both sides of the interface. And it turns out the tangential components and normal components have different boundary conditions. So to get the boundary conditions for the tangential components, we'll use this line integral E dot dl. And here is the integral, the path we'll take to do that line integral. And notice that spans the interface. We have to do that in order to extract the information from this equation that's telling us what happens at those boundaries. So while that's a rectangle and has 4 sides, in fact we have to divide this into 6 separate integrals because 2 of those sides are divided by the interface. So if we do a line integral and we start at A, we'll integrate first from A to B, and that's no problem because it's all in the same material. We'll then integrate from B to 0, then 0 to C, C to D, D to 0, and then 0 to A. So 6 separate line integrals make this single closed contour line integral. Now if we go one term at a time, this is what we get. So when we're integrating from A to B, this is tangential to the interface. So the field is simply E1 tangential. And the length of that is delta W. So this first integral is just E1 tangential times delta W. Now the second integral, we're going from B down to 0 of E dot dl. Since we're integrating in the normal direction, that's E1 normal. And then the length, the total length of this side is delta H, so the length of this integral just from B to 0 is delta H over 2. Notice there's a negative sign out there. That's because the positive direction is upward, but we're integrating backward. So we put a negative sign here. Okay, now we integrate from 0 to C. That's also integrating in the negative direction, so we have a negative sign out here. We're in the second medium, so it's E2 normal, and then the length of that line integration, delta H over 2. Okay, now we're at point C. Now we integrate from C to D. Well, that is the electric field along here is the tangential component, so it's E2T, and the length of that was delta W. So we have a delta W, and we have a negative sign because we're integrating in the negative direction. The positive direction is left to right here. Okay, now we're at D. Now we're integrating in the positive direction, so we'll see the remaining 2 integrals have a positive sign here. We're integrating in the perpendicular direction, so both terms will contain normal components. So this first integral from D to 0 has a length of delta H over 2, and the field is E2 normal because it's in the second medium, and length delta H over 2. And then finally from 0 to A, we have E1 normal, and then the length delta H over 2. So that was a lot of work, but we now have our line integral spanning the interface. At this point, we can look at a bunch of terms and realize that a bunch of things cancel. We see this term repeats itself, once positive, once negative, and so does the other term. So they cancel, and we're just left with these 2 terms containing the tangential components of the electric field. So from this, we conclude that the tangential component of the electric field intensity E is continuous across the interface. It's important to understand this is the E field and not the D field. The electric flux density we'll look at next. So now let's derive a similar boundary condition for the electric flux density. Fortunately, we've done all the work. Almost all the work. We start with our boundary condition for the electric field intensity, and then we apply the constitutive relation to that. And we simply d over epsilon equals our electric field intensity. So this is our boundary condition for the tangential component of D. So the tangential component of D is not continuous across the interface. That is discontinuous. However, the ratio of the tangential component of D to the permittivity, that ratio is continuous across the interface. The fact that that ratio is continuous doesn't mean much to us in this course, but there's another class, computational electromagnetics, where that fact really helps us improve numerical simulations of things. But it's not something we need in this class. But we do need to understand that tangential component of E is continuous across the interface. Tangential component of D is not. Now on to the boundary conditions for the normal components. This is where we'll place a surface charge at the interface between these two materials. Then we'll construct a pillbox that spans the interface. And this little elliptical region here, that's the cross section of our pillbox that lies on the interface. The area of the top and the bottom we will call delta S, and the height of this pillbox we'll call delta H. And we want to integrate the electric flux on that pillbox. So that cylinder, the pillbox, really has three sides, or we need to integrate this on three different sides. It has the top, the bottom, and then, I don't know, some people maybe count this as an infinite number of sides, but on the side. So we have top, bottom, and then around the side of the cylinder. We write that as three separate integrals, and we can handle those separately. So when we calculate the flux on the sides of the cylinder, this delta H term, we're going to let that go to 0. And in fact, the flux from that also vanishes. So we're really just left with the flux leaving from the top and the bottom of that pillbox. So what that is, we're calculating flux, so we're only listening to the component that's punching straight through that surface. That is the normal component of D. And so if we integrate across the area delta S, we just get a D1 delta S. Now down here, the field is pointing downward in the negative direction, so we have a negative sign here, D2N delta S. So the total charge is rho S times delta S. And how do we get that? Well, we derive this when we're talking about charge distributions. Total charge is the surface charge density times the area. So we actually have an expression for total charge. We can then equate this expression to the expression we just derived by integrating the flux. So we set these equal, and then we can divide both sides by delta S, and in fact, we'll be at our boundary condition then. So that is our boundary condition. The difference between the normal components of D is our surface charge density. Now, very often we will analyze things without there being a charge on the surface. So in fact, more often, we just write it this way. And this says that the normal component of D is continuous across the interface. Before, we had the tangential component of E was continuous. Now we have the normal component of D is continuous, but remember that's only continuous when there is no charge on that surface. Otherwise, we have to resort to the more general boundary condition. So what about the normal component of the electric field E? Well, we've done most of the work. All we have to do is apply our constitutive relation and write this in terms of E. And so when we do that, we see that epsilon 1 times the normal component of E1 minus epsilon 2 times the normal component of E2 is the surface charge density. Now when surface charge is 0, which is most of the time when we're analyzing things, we see that we just have the product of the permittivity times the normal component of the electric field is continuous across the interface. The product is continuous. So the normal component of the electric field E is not continuous across the interface, but the product of permittivity times the normal component of E, that is continuous across the interface. Now we need to talk about the refraction of static fields at a dielectric-dielectric interface. And this is relating the angles of those fields. We're calling this refraction. It is refraction, but this is not to be confused with Snell's law, which describes the bending of a wave at an interface. We're not talking about waves, we're talking about static fields. They still appear to bend, but in fact it's a completely different rule that they follow than Snell's law, and the bending looks different. So here's how we're setting up our problem. We have the same interface. We're setting up E1 and E2, D1 and D2 on either side of the interface, and we're also showing the tangential and normal components for all of these. And just like before, we have medium 1 with permittivity epsilon 1, and medium 2 with permittivity of epsilon 2. That's our setup. What we're adding now is the angle of these. And so those are always measured off of the surface normal. The surface normal is a direction that punches straight through the interface, that is perpendicular to the interface. So this direction is the surface normal, and the angle of E1 and D1 is measured off of the surface normal, and we call it theta 1. E1 and D1 are always in the same direction because they're related through the constitutive relation D equals epsilon E, and epsilon for isotropic materials is just a scalar. So D and E are always in the same direction, so they have the same angle. And I can say the same thing about D2 and E2. They're in the same direction, so they have the same angle. And that angle theta 2 is also measured off of the surface normal. Now we can write our fields, the electric field E on either side of the interface, as the sum of the tangential component and the normal component. And we do this for both sides of the interface. However, if we know those angles, theta 1 and theta 2, we actually have expressions for the tangential and normal component based on the magnitude of the electric field. So we'll call the magnitude of the field in medium 1 is just E1. So the tangential component of E is E1 times sine theta 1. Likewise, the normal component then would be E1 times cosine theta 1. And we can do the exact same thing in the second medium. The tangential component of the electric field in the second medium is the magnitude of the electric field in the second medium, E2, times sine theta 2. And then the normal component is E2 times cosine theta 2. Now that we have expressions for our tangential and normal components, let's apply the boundary conditions. We know that the tangential component of the electric field E is continuous across the interface, so the tangential components must be equal. So we can conclude that E1 times sine theta 1 has to equal E2 times sine theta 2. We also have the normal components. For the normal components, it's the product of the permittivity times the normal component. The product is continuous across the interface. Let's throw in our expressions for the normal component, and we end up here. Epsilon 1 times E1 times cosine theta 1 equals epsilon 2 E2 times cosine theta 2. At this point, we have two equations, and we can use these to eliminate E1 and E2 from the equations, and we'll just have the epsilons and the angles in a single equation. That is our law of refraction. Okay, so those are the two equations that we derive from our boundary conditions. Now what we can do is divide those equations. So we'll have E1 sine theta 1 divided by this expression, E2 sine theta 2 divided by this expression. Now we notice that the E1s cancel and the E2s cancel, and the sine over cosine is tangent, and that is our law of refraction for electrostatic fields. We don't need to know what the electric field is, we just need to know the angles and the permittivity in each medium, and we can calculate the angles. And we'll do this when we get to our example. So that's the law of refraction. Can't talk. This is the law of refraction, but it is not Snell's law. Snell's law deals with waves, and we're not dealing with waves here. This is static fields. Okay, our last handling of boundary conditions before we move on to our example. This is for a dielectric conductor interface. So to analyze a dielectric conductor interface, we have the same setup that we had for the dielectric interface. What I did is I changed the color down here to something more like copper to remind us that this second medium is a conductor. So let's assume that we have infinite conductivity. This is a perfect electric conductor. Let's think about what that means for Ohm's law. So inside the second medium, the current density will be the conductivity times the electric field. So let's just say we have a reasonable electric field. Let's say it's 1 volt per meter. Well, if we have an infinite conductivity, that would mean we also have an infinite current. That doesn't seem reasonable. And in fact, that can't be. And so it's for this reason that we conclude in order to not have an infinite current in a conductor, the electric field inside of a conductor has to be 0. And then if we tie that back to our discussion with the electric potential, that means whatever the potential is inside the metal is the same value everywhere. It is constant. The potential doesn't have to be 0. It just is constant everywhere. And then the gradient of that is the electric field, which is 0. So that brings harmony to all this stuff. So the electric field has to be 0 inside of a conductor. That prevents the current from becoming infinite. Now let's look at our boundary conditions. Inside the conductor, the electric field is 0. That means that the tangential component of the electric field in the second medium has to be 0. What does this mean for the electric field in the first medium? That means that the tangential component inside the dielectric right at the interface also has to be 0. Now the normal component has a different boundary condition. It does not have to be 0. So if the tangential component is 0, that means the electric field always at the interface with a metal is normal to that interface because there is no tangential component. So the electric field is allowed to have some value right up to the conductor, but right at the conductor, the angle is 0 degrees. It is perfectly normal. So we'll end our theory discussion with some final notes about perfect conductors. First, there can be no electric field inside of a conductor, and we can explain this two different ways. If the potential is constant throughout a conductor, that's something we learned in circuit theory. The electric field is the gradient of the potential, and so the gradient of a constant is 0. We also saw through Ohm's law that there can't be an electric field because that prevents the current from becoming infinite. And then restating that again, if the electric field is 0, that implies the electric potential is constant throughout the perfect conductor. And last, at the interface with the metal, not necessarily some distance away, but right at the interface, the electric field is perfectly normal to that interface. There is no tangential component, and that's because the tangential component has to be continuous across the interface, and the tangential component inside the metal is 0. Now let's work an example to reinforce all of this. So example number 1. we have an interface between two different semi-infinite media. What semi-infinite means is we have an interface, but each one of them on their side of the interface extends off to infinity. And the dielectric constant of medium 1 is 2, and in the second medium, the dielectric constant is 4.4. So question number 1. If the electric flux density, so that's the D field, in medium 1 is this expression, calculate the electric flux density in medium 2. Then question number 2, what is the angle that D1 makes with the interface? And then question number 3, using the law of refraction, calculate the angle that D2 makes with the interface. So we have 3 questions for this problem. Let's dive into this. So I like to start by drawing the problem. Now this is a 3-dimensional problem, so I'm drawing in 3 dimensions. If this were a homework or something, I would probably only work this in 2 dimensions. But we can do 3 dimensions here. So we set up our problem. Then we'll plot the first field. That's the D field in medium 1. The basic strategy is we're going to decompose this D1 into tangential normal components, then apply the boundary conditions separately to get tangential and normal components of D2, and then reassemble that answer. So right away, we can write the tangential and normal components of D1, and we've also plotted those in our figure to the right. So first, we apply the boundary conditions to the normal component. This is the easiest one because the normal component of D is continuous across the interface. So that means whatever it is on the first side, it's equal to the second side. And we have a number for the first side. That was a given. So we already know the normal component of D in the second medium. It's 1.5 in the z direction, pointing upward. Then we look at the tangential components, which is a little bit more complicated boundary condition because we have the permittivities here. Solving this for the tangential component of D in the second medium, and we just get the ratio of the permittivities times D1. That's not too bad, and we can plug in the numbers that we have now. So we have the ratio of our permittivities, we have the tangential component of D1, and that makes our tangential component of D in the second medium this expression. So we applied our 2 different boundary conditions. We now have the normal and tangential component of D. All we have to do is reassemble them to get the overall D2. So that's exactly what we do. We just add them together. And there's our D2. And we plotted it over to the right as well. Draw a box around it, and we can say that we're finished. So remember the strategy. We wrote D1, we decomposed that into normal and tangential components, we then applied the boundary conditions on those separately, we got the field in the second medium, and then we reassembled, and we have D in the second medium. Now we want to calculate the angle of D1. And remember, the angle is always measured off of the surface normal. So how on earth do we do this when we have this strange arbitrary vector in full 3 dimensions? Well, remember the property of dot products. If we can calculate the dot product of 2 vectors, that dot product will equal the product of their magnitudes times the cosine of the angle between them. This could be the angle that we want to find. So we let A be D1, we'll let B be the surface normal, and then that theta AB will be theta 1. That's the angle between them. So the dot product is D1, dot product with the normal component AZ. That has to equal the magnitude of D1 times the magnitude of our normal vector times the cosine of the angle between them. Okay, so that's the equation we had from the previous slide. Let's start putting in what we know. So D1 dot product with AZ just gives us the Z component of D1. That has to equal the magnitude of D1. This magnitude of the normal component is just 1, so we don't even have to write that. Times cosine theta 1, And we can solve that for cosine theta 1. That's just the inverse cosine of dz over d1. We can plug in our numbers, and we get an angle of 55.9 degrees. Now for the angle of D2, which is the third question, we could go through this with the dot product again. But we've already done that, we've illustrated that. Let's practice and calculate that angle using the law of refraction. That should be easier. So let's go ahead and calculate the angle theta 2 of D2, and theta 2 is also measured off of the surface normal. So we're going to use the law of refraction. Remember, this is not Snell's law, that's for waves. And we can solve this for theta 2, which is the angle we're trying to find, and then all we have to do is plug in the numbers for our permittivity and the angle we just found, that was 55.9 degrees. So we plug in our numbers and we get 72.9 degrees for theta 2. So the problem's been solved. This is a lot easier than going through the dot product, but had we gone through the dot product, which would be a good exercise for you to do, that should be the answer that we get.